Good morning to one and all. I'm Parthiban, working as an assistant professor with the Department of EC. Now I am going to talk about the subject called electron devices, which is coming under the regulation R2020. The subject code is EC25C01. Now I'm going to talk about the topics called special diodes. So under this, I'm going to talk about the tunnel diode, which is also called as Iseki diode. It was introduced in the year 1958 by Leo Iseki. It is a heavily doped p-n junction diode. Generally, it is operates based on the quantum mechanical effect known as tunneling. Unlike an ordinary p-n junction diode, the tunneling diode has an extremely high level of doping. The impurity concentration is approximately 1 part in 10 power 3 atoms compared to 1 part per 10 power 8 atoms in the normal case. Because of this heavy doping, the depletion region becomes extremely thin and approximately around 100 angstroms. Tunnel diodes are commonly made from the materials such as germanium and gallium arsenide. The most important feature of tunnel diode is that it exhibits a negative resistance region due to the tunneling phenomenon. The symbol is shown in the diagram. What is tunneling? Why it is needed? In the classical physics, a charge carrier such as electron must have an energy equal to or greater than the potential barrier height to the cross the p-n junction. However, according to the quantum mechanics, the barrier width is extremely thin, then there exists a finite probability that an electron can penetrate through the barrier even if its energy is less than the barrier height. This phenomena is called quantum mechanical tunneling. In the tunnel diode, because the depletion region is extremely thin due to heavily doping, the electrons can tunnel directly through the junction. This tunneling effect is generally a fundamental in operating principle of tunnel diode. Therefore, it is called tunnel diode or it's also called Iseki diode. The characteristic curve is shown, which shows the characteristic curve between the potential energy versus the space charge region, which is almost in linear in nature. Then coming on to the characteristics of tunnel diode, the VI characteristics of tunnel diode are very different from those of normal diode. Initially, as a forward bias voltage increases, the current also increases rapidly due to the tunneling phenomenon. This current reaches a maximum value called the peak current, denoted as IP, at a voltage called peak voltage, which is denoted as VP. Beyond this point, the forward voltage increases further. The current decreases instead of increasing. This region is known as a negative resistance region because an increase in the voltage results in the decrease in the current. The current reaches a minimum value which is called valley current or it's also called IV. The voltage at that point is called valley voltage, that is VV. After this region, the diode behaves as if like a normal diode and the current increases again with voltage. The presence of the negative region makes the tunnel diode very useful in the high frequency oscillators as well as in switching circuits. Next, we are going to see about the energy band diagram of xenon diode. At zero bias, the Fermi levels of p-n junction align due to heavy doping. The conduction band in the n region overlaps significantly with the valence band in the p region. Because the depletion region is so very thin, the electrons can tunnel across the junction even without the external bias. However, the net current flow at zero bias is zero because equal tunneling occurs in both directions. So this is the difference between the xenon diode and the tunnel diode. Next, we are going to see about the energy band diagram for a small forward bias voltage. You see the energy band diagram at zero bias. What will happen? When a small forward bias voltage is applied, the energy band shifts very slightly. Now the electrons in the conduction band of the N region find available abruptly empty states in the valence band of the P region. This alignment increases the tunneling probability and a large number of electrons tunnel through the barrier. As a result, the tunneling current increases rapidly and reaches the peak current. This corresponds to the peak point in the VI characteristics. Next, we are going to see about the energy band structure when the maximum tunneling current occurs. At the peak voltage, the alignment between the filled states in the N region and the empty states in the P region is maximum. This results in the highest tunneling probability and hence the maximum tunneling current, which is known as peak current. Beyond this point, the further increases in voltage will reduce the alignment, whereas decreasing the tunneling probability. That we have to take into account. Then, coming on to the energy band diagram again, when the forward voltage is increased beyond the peak voltage or maximum, we can say, the alignment between the energy band reduces significantly. As a result, fewer electrons can tunnel across the junction and the tunneling current decreases. This creates a negative resistance region. Eventually, at even higher voltages, the normal diode conduction dominates and the current increases again due to the diffusion of carriers, which is very similar to a conventional diode. And then we are going to see about the tunnel diode equivalent and its properties. For example, the tunnel diode operation can be made equivalent, or we can say analogy, by including the negative resistance component along with the small series resistance and capacitor. This negative resistance region represents the negative slope of the VI characteristics. Because of this negative resistance property, the tunnel diodes are widely used in microwave range of frequencies, particularly as oscillators, as high-speed switching circuit, as well as amplifiers operating at very high frequencies. So the main application of tunnel diodes in the microwave range, particularly the very high range of frequencies. Then coming on to the various other features, that is across the applications of tunnel diodes, due to its extremely fast response and negative resistance characteristics, the tunnel diodes are used in very high frequency oscillators, microwave amplifiers, as well as for ultra fast switching circuits. It is also particularly used in memory storage devices, as well as the important application called relaxation oscillators. So the ability to operate at very high frequencies makes it suitable and ideal one for microwave range of communication devices. So for further, we can see the principles of electronics book, which will be very useful for referring the topic, as well as the electronics fundamentals and application book, which is also very useful. So I have referred all this book for studying about the quantum mechanical tunneling effect. It has an extremely thin diffusion layer and it exhibits a unique negative resistance region characteristics in its VI characteristics. This special property makes this tunnel diode is very highly useful in high frequency range as well as in the microwave range of applications. Understanding the operation of tunnel diode is well achieved by means of studying the above reference books. Thanking you one and all for hearing my lecture on tunnel diode and its applications. Thanking you one and all for once again, thank you. Thank you much.